Welcome, welcome everybody to day 3 afternoon session, and we will start with speaker Jenny Nelson. She will talk about impact of chain conformation on charge transport in conjugated polymers. Jenny, the audience is yours.
Hey, thank you, Marcus, for the introduction, and many thanks to Jochen and his team for organising this meeting. It looked like a very exciting meeting when Jochen talked to me about it, probably back in 2019, and I'm very happy it finally came to happen. It would be much nicer, of course, if we had it in person and we could all get together in London, because it's a fantastic program. Even though I'm in London, I would rather everybody else was there as well. Okay, so my talk's going to be about transporting conjugated polymers, and the work is really, I'll explain different people's roles as we go through, but I'm happy to say it's been a nice sort of collaboration, particularly with other labs, some other labs in Europe, and collaborator in the US as well. And the context really is in practical applications in organic electronics. We often want to work with conjugated polymers for the advantages of the processability of the materials. And conjugated polymers, of course, introduce some complexity in terms of understanding charge transport. So we can really think about it in terms of two contributions: a contribution of charge transport along the chain and charge transport between the chain. And those two regimes of transport involve slightly different phenomena to think about. So in the case of, if we think about what controls intra-chain charge transport, it has a lot to do with the geometry of the conjugated polymer itself that will control effectively the shape, and the geometry and the torsional potential together will control the shape that the polymer has, and also its conformational phase space. And as well as that, we care about what the intrinsic sort of transport of polarons along the chain, which will be strongly influenced by the electron-phonon coupling. And normally this happens in a regime where you can't assume a hopping model and need to use some kind of non-adiabatic or quantum model. In the case of interchain transport, then we care about how two chains, how the chains pack in the solid, whether that's in a crystalline or amorphous manner, and particularly about the interactions between chains when they come close together, close enough for charge transport to occur with a reasonable rate. And when that happens, it's usually happening at a slow enough rate that it's fair to use a semi-classical treatment such as Marcus theory, and then you would care about the electronic coupling at that point, the reorganization energy, and that would give you an estimate for the rate of charge transport. So the whole picture is there's quite a lot of different things we need to think about, and it's relevant to think about whether intra-chain or interchain phenomena are limiting charge transport. So another thing I want to comment right at the beginning is that when we try to explain experimental data, it's worthwhile paying attention to what exactly the measurement that you're looking at is probing. So I've given some examples here of different types of mobility measurements that we and many other people have used, and they're basically probing sensitive to sort of rather different sets of parameters. And without going into anything in detail, I would simply make a point that if we can use multiple methods together on the same material, that can be very helpful in pinning down the mechanisms and the relevant parameters to explain charge transport. So what I'm going to do today is I'm going to talk about examples of two systems and look at a set of experimental data and the approach that we use to try to explain what's going on. And the first example is a case of a polymer where we were able to look directly at the effect of conformation on the intrachain transport, and in a case where intrachain transport is limiting the observations. And the polymer here the polymer that we study here is a relatively simple polymer. It's a sort of well-known, widely studied blue emitting polymer with fluorine with octyl side chains, often called PFO, sometimes called PF8. And in terms of the parameters I just mentioned, so its geometry is, it's got a slight twist in the backbone. It means that in general, the polymer is non-collinear. It's also non-planar because the consecutive monomers have got this phenyl-phenyl linkage. That means the ground state geometry has a twist of about 45 degrees in the chain. And the combination of these two effects is that the conformation that a chain can occupy can be quite space-filling. The polymer also in a solid state adopts different phases. It can be crystalline, it can also be glassy, and it has liquid crystalline phases. And a sort of possibly not very surprising consequence of that is that when you look in the literature for measurements of the hole mobility in PFO, you find there are a lot of different numbers, in fact, spanning orders of magnitude. And that's partly because of the different phases in which the polymer may exist, and partly, of course, because different measurements are probing transport in different ways. So we wanted to try to bring some, try to understand a little bit better what's going on with this polymer. And we focused on this question of what happens when you introduce a particular conformational defect into the polymer. And this defect is known as the beta phase. And what it means is that whilst in the ground state of a polymer chain, you have these, the monomers contain normally accommodated a torsional twist of 45 degrees-ish or 135 degrees-ish between consecutive monomers. You can introduce a defect into the chain where you have a number of monomers that are coplanar with one another. And that defect is metastable in the sense that the total energy of the oligomer is then not in its minimum configuration. However, it stabilizes the electrons and holes with the consequence that the homo-LUMO gap is reduced in the beta phase. And what that means from a practical sense is it's very easy to see it because it introduces a redder sort of component to the optical spectrum. You can see it in absorption and emission, and so it's quite easy to do experiments where you know beta phase is there, beta phase is not there. Okay, you can introduce beta phase by allowing the polymer film to interact with a solvent like toluene, giving the polymer some free volume, and then a small fraction, maybe 5% or 10% of the polymers might adopt this conformer. Now, the interesting thing is what happens to charge transport. So if you take a film of PFO and you introduce beta phase, you find it slows down the charge mobility when measured by time of flight by between 1 to 2 orders of magnitude. That's quite significant. And we also looked at the impact using different measurements, and we find that in a sort of steady state measurement, actually using impedance spectroscopy, the beta phase shown in red reduces the hole mobility here, maybe by not so much, by about half an order of magnitude. But if you were to look at the intra-chain transport using a technique like time-resolved microwave conductivity, introducing beta phase actually increases rather than decreases mobility. So clearly the effect is method dependent. And then if we want to try to make sense of all of this, the picture that we came up with is one where we propose that the beta phase segment will act as a trap. So in this component, because of the higher electronic coupling between consecutive units when they're planarized, the energies for the electrons and holes are stabilized, and this long beta phase then introduces a trap for the holes. So we can think about what that would do to the density of states, and from that try to think about what the quantitatively what the impact would be on the landscape, which is seen by moving charges. So for this, we use a kind of one-dimensional tight binding approach, and we argue that the electronic coupling varies like the magnitude of the cos theta, the torsion angle between consecutive units, and this between in the optimized chain, that torsion angle is around about 45 degrees. In the beta phase, it's 180. And then when we pop those numbers into this one-dimensional tight binding model, you see that the effect, and introduce a certain amount of energetic disorder as well. We see that the effect, sorry, not energetic disorder, just a certain amount of torsional thermal disorder in the torsion angle in both cases. We see that the effect of introducing the beta phase is to introduce these defects which lie at an energy B. These are holes, so they're at an energy above the HOMO of the unplanarized film, and as such they would introduce a trap, which we estimate this from the calculation of the electronic coupling between the consecutive units as a function of their torsion. We use that estimate. We put that into the model, and we extract the effect that the beta phase would introduce a trap that's 200 or 300 millivolts deep, as seen by the holes into the density of state. So that's something that you would expect to be visible in experiments at room temperature. So we look for the density of states in two ways. And one is to take very high dynamic range photocurrent transients, where we basically follow the photocurrent over a long period in time, as going out, beyond milliseconds, and then interpret those transients in terms of the release of charge carriers, holes in this case, from the density of states. And then you can obtain a map of the density of states. And when we do that to our experimental data for films with and without this conformational defect present, we find that the defect appears to lie some 0.3 millivolts deeper than the absorption edge, than the mobility, than the density of states edge for the glassy film. Then, in collaboration with Wojtek Nadazdi in Bratislava, we were able to look at with a different method at the density of states for the two different types of films. And this is a method called energy resolved electrochemical impedance spectroscopy that he's developed. And with the method, we could see again, there is evidence of a defect, a fairly pronounced defect lying about 0.3 electron volts below the edge of the density of states for the glassy film. So this is sort of telling us, okay, it looks as though the transport ought to be affected by some defect in the density of states lying about 0.3 eV below the edge. So we then plugged that into, to see if we could explain our device results, we plug that into a model, it's a drift diffusion model in which the energies of charge carriers are resolved, so we can look explicitly at trapping and release from the density of states. It was developed by Rod Mackenzie, now in Nottingham, and using that code, we could then by modeling the data for the glassy film and then introducing the density of states, we could reproduce the effect of the beta phase defect on both the time of flight data and on that sort of a more sort of far from equilibrium measurement, if you like, and on the steady state impedance spectroscopy data. So in both cases, the beta phase reduces the apparent hole mobility, and by a different degree, depending upon the type of measurement. So that was really the message from the first part of the talk, that a beta phase conformer introduces a trap that limits mobility, and different mobility measurements can be reconciled using a single model. So then Obviously, we would not like to be in a position where transport in conjugated polymer is limited by defects within the chains. We would rather be in the case where intra-chain transport is irrelevant. And the next case, the next example we look at is an example of that case. We're going to look at the case of this polymer C16 IDTBT. It was actually mentioned by Henning in his talk on Monday as being a very high mobility conjugated polymer, and one that's interesting because unlike other previously known high mobility polymers, it doesn't crystallize. And what's interesting about, well, what's, I suppose, a sort of a prerequisite, if you like, to avoid the problems of PFO would be to avoid the situation where conformational variations in the chain would lead to a broadening of the density of states. In the case of PFO, because of the phenyl-phenyl linkage, the ground state torsional angle is far away from the angle at which the electronic coupling would be maximized, which would be when the plane is flat. But in the case of something like IDTBT and many other polymers where you have a thiophene involved in the linkage, this sort of phenyl-phenyl linkage problem is avoided, and you can find a lower energy configuration close to 180 degrees. And in that situation, then the ground state geometry coincides with the case when the electronic coupling is the highest, and then having torsional disorder in the polymer is not likely to introduce to broaden the density of states by a great deal. And so the impact of torsional disorder on the energetic density of states is going to be more slight. So we expect IDTBT to be good for that reason. As it's been mentioned already on Monday, it has a high FET mobility of 1 to 4 centimeters, order of 1 centimeter square per volt second, and it's been reported to be a trap-free polymer. So question is, of course, then what is now limiting hole mobility in C16 IDTBT? Now, the first thing I would say here, so of course we're going to start thinking about interchain contacts. And maybe the first thing to say here is that when we use spectroscopic probes to look at the interchain contacts in C16 IDTBT, we find that really there's not a lot of evidence of strong interchain aggregation. So these are absorption and luminescence spectra, and together on the same axes, we're looking at the absorption spectrum of the film, that's the red and the blue, that's before and after thermal annealing, and the absorption spectrum of the same polymer in solution. And here the same data for the luminescence. And what you can see is, unlike many other conjugated polymers, there's actually not a strong impact of solidification nor of annealing on the spectra. The absorption and emission of the polymer in the film is rather like what it is in solution. The chains don't interact a lot, apparently. Not surprising, because they have such huge, bulky side chains attached to them. Similarly, when we look at the temperature-dependent Raman spectra, we see very little effect of temperature in the spectra, which again suggests that the polymers are not aggregating or interacting strongly with one another. So now that means that we could then sort of try to disregard a high degree of chain aggregation as being the thing that limits transport. So then we would like to try to learn something about what does the density of states look like. Now, it's already been mentioned that the Henning made a reference to on Monday to this paper where the transport was reported to be trap-free. When we look with the methods available to us, so we look with our electrochemical impedance spectroscopy with Wojtek, so the density of states that we can detect is probably limited by the resolution of the measurement, but it certainly looks less than some tens of MeV. And also when we pull out the range of torsional angles and see what degree of energetic disorder we expect from those, this is from an MD simulation that I'm about to mention, we find again that any energetic disorder due to the torsional disorder is going to be only a couple of tens of MeV. So we don't expect a high degree of energetic disorder. Now let's look at the transport data. So FET mobility, I'm using here data, very nice data collected by Sam Schott from Cambridge in a paper a couple of years ago. They presented the temperature-dependent FET data. It's weekly temperature dependent, and also the magnitude at room temperature compared to PFO is about 2 orders of magnitude higher. When we then look at other techniques, so we don't have time of flight measurements for C16 IDT-BT data yet, but when we compare a sort of an equivalent time-resolved SCLC measurement with time of flight for PFO, they're comparable, but they're different measurements, so we can't draw many conclusions. When we look at the more quasi-steady state measurement using impedance spectroscopy, we find IDT-BT is about an order of magnitude better than PFO. And then when we then looked with Matt Bird in Brookhaven National Laboratory at the Interchain mobility in solution, and all he could say was that it is larger than 1 centimeter squared per volt second, and that is already about a factor of 3 higher than it is for PFO. So this polymer, which is definitely not limited by intrachain transport, is better than PFO. It might then be, but the comparison depends on the method, and it might then be surprising that the mobility is not actually higher than that. So then we decided to explore this using a combination of methods. So we wanted to build representative structures on which we could do transport simulations, and we did that. And then we after having done that, we then explore the intra-chain mobility and try to compare that with the measurements on chains in solution using the time-resolved microwave conductivity. And we also build a solid-state assemblies in which we can simulate the charge transport, and we can take advantage of the possibility to model transport in the vertical and lateral directions. So the structures were made by coarse-grained molecular dynamics. It was a work of Anders Kertsen, who was a PhD student in DTU in Denmark, and he built an atomistic force field, mapped it onto a coarse-grained force field using the Martini approach, and then carried out simulations both of chains in solution. And you can see from this that actually the chains are rather stiff, and even over a 5 nanoseconds period, they don't change in conformation a great deal. And he also simulated the solidification of the chains by evaporation onto a substrate. And then we used these structures to try to simulate transport. So the first thing was to try to simulate transport in the single chains. Now, given everything else that's been discussed this week, I can hardly say that it's reasonable to consider that transport along the chain will occur by hopping. However, we did that because it allows us to model the whole system on a single sort of graph-based transport. But at the same time, we also checked that the intra-chain transport parameters actually have no effect on the final results, or minimal effect on the final results, so long as they're fast enough. So we sort of used the approximation, which I know is a poor approximation of hopping, to model the experimental data for transport along the chain. And all we can really say is that it pins down to some extent the parameters that we would use to make sure that our mobility is faster than the lower limit that is extracted from the measurements. And then with that constraint, we go on to model interchain transport. So we extract our structures from the coarse-grained MD. We then identify contact points, and we then calculate the interactions between the chains at the contact points and build up a distribution, which of course will depend on the precise organization of those chains near the contact points, and then we can synthesize a distribution of interchain couplings, and then we need finally the reorganization energy, which we obtain from calculations of the study of the vibrational modes of the molecule. And we find actually the reorganization energy for Hall transfer is relatively high in these materials. Then we can finally model hopping transport on the networks that we simulated with MD. And then there's a couple of things to say. Now, the first thing, here we're looking at the Hall mobility as a function in a sort of so-called Pull-Frankel plot, as a function of the electric field. We have some experimental data just down here, and two things. So, Marcus, I have about 2 slides. We have, so we've got 2 things to observe here. One is that there's a significant anisotropy in the Hall mobility, in that the transport in the lateral direction is, and the X and Y direction is an order of magnitude or so larger than in the vertical direction. And secondly, there's an effect of the molecular weight of the polymer. In our coarse-grained MD, we can only go up to chains that are maybe something like 20 or 30 repeat units long. It's still short compared to the experimental polymers, but we notice that the anisotropy gets more severe as the chain gets longer. And then the second thing is that when we then try to reproduce the temperature dependence of the FET mobilities, we find we can do that, and that almost all of the temperature dependence is due to, or can be explained by the reorganization energy involved in the intrachain hop between separate chains. And so it seems that the reorganization energy is one of the things that may be limiting charge transport in this polymer. A final point here is that the impact of the intrachain mobility is minimal. Now, I had one more piece of data. Because I'm out of time, I'm going to jump over it and simply tell you that as a, if somebody's interested, they can ask in questions, but as a sort of a complementary piece of information about this class of polymers, we find they seem to be able to support spontaneous charge pair generation in solution. So to conclude, my points would really be that, first of all, in terms of measuring mobility, particularly in conjugated polymers, measurements are any single measurement is seldom foolproof. We typically need to combine different measurements together in order to try to pull out different mechanisms, and that can be quite useful for trying to distinguish the intra and interchain effects as well as anisotropy. We looked at case studies of 2 polymers. One, we showed that a torsional disorder could lead to traps in non-planar polymers, so I guess we should avoid those. And then, through a study of the IDTBT, we came to the conclusion that planarizing the polymer alone, although we can do that quite well, it won't lead to super high mobilities. We still are going to be limited by the interchain hopping rates and reorganization energy. And conceptually, I don't think any of this is new, but still, it's nice to be able to pin down into what's going on in different material systems. And finally, I'd like to thank my co-workers, and particularly Xingwan and Jack and Anders, and I'd like to thank you for your attention.
Okay, Jenny, thank you very much for this very nice talk. I have 2 questions in the chat. One is from Oleg: can the trap part of the DOS for the beta phase of polyfluorene be understood in terms of a metastable in polaronic state? So he's asking about the trap. This may be a polaronic state.
We have, I mean, I suppose it's a question saying whether or not the defect would be there if the state wasn't occupied.
Yeah.
Yeah. I mean, I think to our measurements, because we were able to. I mean, my feeling from the set of measurements that we've done is that it is not. The beta phase is quite evident in a number of different number of different measurements that are kind of consistent with each other. So, for example, when you do the absorption and luminescence spectroscopy, it's consistent with there being a transition there, and that transition it has got the energy that you would expect from having had a physical defect, whether it's occupied or not. I'm imagining that we wouldn't see absorption into the beta phase state if it was only present when it was occupied by a hole. And then I think also the EIS spectroscopy probably wouldn't pick it up in the same way if it was only a polyronic defect. But I have to say that I'm not sure from the question that I fully understand it. So I'm more than happy to chat with Oleg offline.
Maybe you. So I give you another question if you try to be quick on this, and you have to answer Jochen in the chat. So that's from Abhishek. How do you get back to atomistic model from coarse-grained when you want to calculate the interchain couplings?
Okay. So basically what we do is this. So we first of all we have to build a map to go back from coarse-grained to atomistic, and that requires a little bit of work to do that. But we have it, and then having gone back, we then need to. So we basically need to avoid any, if you like, quantum mechanical mistakes that might have been baked in through the MD, which is basically classical. So what we do is we relax the structure using a few steps of an optimization with DFT, and we also watch the conformation. So we typically would relax say if you have a pair of, we might chop off trimers, for example, around a contact point, then relax that trimer together for maybe 1, 2, 3 steps in DFT, make sure that they don't unwrap themselves, but they would correct for any sort of accidental bonding or this type of thing that can happen. And then we do the calculation of the coupling using the counterpoise method.
So